Hello, everyone. Welcome to Robotics Café, our weekly online seminar series. It's good that there are more than at least 60 people on the audience. That's nice. As you know, this is an initiative which Aditya, myself, Aditya at Monash, myself at IISc Bhopal, and Sandeep at Plaksha have been talking about this for a long time, and finally we started that we need to have one of these meetings. And with the apart from us, Yogesh and Swadhin at IISc Bhopal, they helped us with all the outreach activities. Yeah. So one of the questions that, especially with the Robotics Cafe, since this is our inaugural session, is so while we were having a lot of discussions with different robotics people inside the country, then we realized that there is a lot of gaps between industry, academia, and the students' connectivity, especially the interaction that is happening at a very sparse. So we thought we want to have some kind of a more sustained interaction between all the three entities. So we thought that how about starting something like an online webinar series that can continuously have this momentum going, and people can interact and know each other, at least in a virtual way, and what their work is all about. And in the same line, what we also thought was we need to give some kind of an forum for students to discuss and talk about their research, which can help them in gaining potential collaborators as well as future employees. And in keeping that aspect in mind, so what we have is in the entire 1 month series, we will have talks from faculties and from industry, as well as from 2 students across the country. Will allow them to give their works so that they can get a better visibility. Yeah. So that's the in short story of our Robotics Cafe, and finally we are here. So I'll now let Aditya to introduce the speaker.
Thank you everyone for being here. It's good to see the audience here. So Professor Debasish Ghose is an honorary professor at the Indian Institute of Science in Bengaluru. He was previously a professor at the same institute in the Department of Aerospace Engineering, as well as the Robert Bosch Centre for Cyber Physical Systems. He works in the area of guidance and control of autonomous systems, robotics, and game theory. He has held various visiting positions, such as at the University of California at Los Angeles, the University of Leicester, and the University of Exeter in the UK. He is a fellow of the Indian National Academy of Engineering, the National Academy of Science India, the Indian National Science Academy, AAAI, and he's also an associate fellow of AIAA. So Professor Ghose, it's a pleasure to have you here. It's good to see you, and I'll hand over the floor to you. So folks, just as a bit of housekeeping, if you have any questions, please type them in the chat window for now. It will just keep things a little streamlined. And Professor Ghose can take the questions at the very end, if that's okay. At the same time, though, if you must ask, please go ahead and we'll take it from there. So Professor Ghose, over to you.
Thank you very much, Sujit, Aditya, and Sandeep for inviting me to this very wonderful idea of having a robotics cafe. I must thank all of you that you came up with such a wonderful idea. I believe that any learning will be better if it is not forced upon people. And a cafe is a place where you talk about things in a very casual way, entertaining way, but at the same time, it can generate a lot of interest, storm on a teacup, in this case, a coffee cup. So with this in mind, I have actually kept my talk at a level where it is rather conversational rather than very technical. So I hope you enjoy this. After a lot of thought, I came up with this title, which is AERObotics, the art of catching objects in the air. My other intention, which was rather hidden, is to catch people's interest as well with the title. I hope it has served that purpose. I see that there are quite a few people who have joined online. I hope you will enjoy the talk. And as Aditya mentioned, you can ask questions. I have no problem at all. Please put them in the chat box. Some which needs to be answered immediately, Aditya will let me know. Others I can answer later. With this, let me start. So I'm an aerospace engineer. So although I'm in aerospace engineering, the aero department in Indian Institute of Science is a very liberal department. It allows you to work on many things. So I started working on mobile robots about 25 years ago. So all of us know what mobile robots are. Usually they have wheels or they may be legged, as you can see here in the slide in front of you. And they move around, carry out certain missions. The first picture you see there is a robot that has a camera on top. The one next to it is a robot that can move around and lift things like a forklift. Then there is another robot there which has a manipulator with which it can manipulate things. Then you have a quadruped, a dog created by Boston Dynamics that can walk around like any four-legged animal can. On the right, you see a cartoon of a wheeled robot which has tracks on it. It has various components and so on, and it can carry out many tasks. However, being aerospace engineer, we would like to make these robots fly. So let's look at the next slide. So this is where you have aerial robots, but they are not just aerial robots in the sense that they are things that fly, but they are also aerial robots with active operational capability. So you see there are two of them which have a manipulator arm sticking out of it. One of them is a very flexible elephant trunk-like arm. The other is a standard manipulator. There is another robot here which can do contact inspection of different structures. There's one robot that can act as a surveillance system. So these are actually aerial robots. We are interested in making these aerial robots having manipulative capability. So they can carry out things using manipulators. So let's see how we can do that. So before that, being an aerospace engineer, let me talk about a different problem, which is not really a robotics problem when it started in the 1950s. This is about intercepting targets in the air. So usually when we talk about interceptor and targets, we consider them as point objects. These point objects fly in the air. An interception implies that the interceptor comes as close as possible to the target. For example, consider a missile trying to intercept an aircraft target. So although we know that the missile and aircraft are huge objects, they are usually modeled in this problem as point objects. Why? Because the problem is usually defined in a very large distances. So a missile and a target in these distances, for example, in kilometers, can be considered as just a point object. So long ranges, and also the destruction of the aircraft is through explosives that have a large lethal radius. So as long as the aircraft is within this lethal radius, it gets destroyed. So the missile, when it comes close to the aircraft, it detonates the warhead and destroys the aircraft. More importantly, they do not have to make actual physical contact. The size or shape of the two objects do not really matter a lot in such cases. This problem has been solved to a very large extent over the last 70 years that people have been doing research on this. So this is not really what we are going to talk about. What we are going to talk about is an AERObotics problem. That is, robots in the air. So instead of a missile and an aircraft, we will talk about an interceptor robot which is used to catch a target robot. What's the important differences between the interceptor problem that we just discussed and this problem? One is the ranges are small. They are not kilometers, they could be a few meters. Physical contact is required between them, but they are risky. Destruction is not necessarily the goal. The information about the shape and size of the target is also important here. The design of the catcher tool, the tool with which the catcher robot catches the target, is also very critical. Remember, it's not a warhead that explodes and destroys the other object. The vehicle and the objects are different from the missile target interception problem. So if you look at the nature of what kind of vehicles we use, they are very different from what we have in a missile or an aircraft. For example, think of a drone trying to capture another drone and bring it down safely. So let us learn from the past. We have solved this interceptor target problem. Many people have worked on it. Hundreds of scientists have worked on it. So what have we learned from that, and what can we use from those into this problem of aerobotics that we talked about? So there are a couple of points that we need to look at. That in the interceptor target problem, the information that is available to the interceptor is basically from a radar. So radars are used to track the target, and this information is used by the interceptor to compute the guidance commands. Whereas in the aerobotics problem, the information is most probably visual, through image, through a camera. And this camera information has to be converted to guidance commands. So this gives rise to a couple of very intriguing questions. One is, will the guidance laws be completely different? Or are the problems so different that they do not have any common basis? Well, it turns out that it is not so, because the basic problem is still the same, no matter what the information is, what the way to, or what the different ways of implementing it is. So let us look at a very simple thing here. Imagine that there is an object A. We are talking about point objects here. An object A and an object B. They fly in the air and they meet at the point given there, which is called the interception. Let me see if I can get a pointer. So this is the interception point where A and B meet. Now, if you just look at this picture, what do you think is the property of this point? The property of this point to make this interception or the meeting possible is that both A and B must take the same amount of time if they started flying at the same time to reach this point. A question that arises is that just by looking at the initial conditions of A and B, can we predict that interception will occur? In this case, it doesn't look like. Of course, the question is loaded in the sense that what do we mean by initial conditions? If we say initial condition means the position and the direction in which it flies, then certainly it is not possible to predict. But suppose there are other conditions also that we know about, then it might be possible to predict interception. For instance, look at the second figure. Here, the object A and B are going around in circles. We all know the equation of a circle. If we know the speed at which A and B are moving on this circle, then we can most probably predict whether A and B are going to meet each other at this point or this point. These are the only two possibilities, right? So we can calculate this, that whether they will meet here or not, because we know they are going around in circles, we know at what speed they are moving, and so on. Remember that in the first problem also that would have been possible had we known what path they are following and what speed at what speed they are moving. In other words, if we know their trajectories, we can predict this. Now let us simplify the problem and look at the third figure. This is where the A and B are moving in a straight line and they meet at this point. And here also, if we have certain information about the initial conditions of A and B and their speeds, we can predict whether they meet there or not. So this part is something that intuitively we all understand very well, that meeting means they must be there at the same time. Let us go to something called a collision or an interception course. So we assume here, now we are making very strong assumptions that let us say A and B are actually, they move at constant speeds, that is given constant speed. Not necessarily same. One can move at say 10 meters per second, the other can move at 8 meters per second. If that happens and they actually happen to meet at this point, then there are certain very interesting things that will happen. What will happen is that the line of sight between A and B will not rotate. They will remain parallel. In fact, this you can see from this figure itself. Suppose I consider the relative velocity VB minus VA in vectorial terms, and this is the point I get, and this is the relative velocity which is along the line of sight. And if this point lies on the line of sight, then A is going to hit B. Right? Very simple idea, relative velocity pointing directly at B. And you can also see that if I take the relative velocity and consider it as two components, one component is along the line of sight, the other component is normal to the line of sight. If I consider these two components, you will see that the one which is normal to the line of sight is 0. And the only thing that exists is the component which is along the line of sight. So this is also a thing that people use when they try to do guidance for these interceptor target kind of thing. Now, what about if they are not point objects? For example, let us say that A is a point object, but B is a sphere or a circle. Whatever I say here in 2D also applies for 3D. It's a circle. Now, let us assume that this circle is moving at a speed of VB in the direction given here, which means that every point on this circle or inside this circle is also moving with the same velocity. Consider the point B1, and suppose B1 moves with the point VB with the velocity VB, and A and B meet at this point, then that is an interception course, but for the point B1, not necessarily for the whole of it. Okay. Let us take a second point, B2. In this case, remember that B1 and B2 both are moving with the velocity VB, same direction, same speed. But to intercept B2, VA has to use a direction of flight which is given here by the dotted line, not the previous one. The previous one would have hit VB at this point, at the point B1. But to hit B2, it would have to go like this. Now, if I want to say that what are the velocities of A that will hit the object B, then I have to take all the points in B and find out what are the corresponding VA directions which will allow this to happen. So if I do that, turns out that I get what is known as the collision cone. So what you see here is a cone. So any velocity vector which is inside this collision cone will hit the object B at some point or other. Right? This is how you define the collision cone. Now, of course, the next question that I would ask, that what's the maths behind it? Can I write down the equations and do this? Of course you can, and you will actually mess up this slide quite a bit if you start writing equations. So let us avoid equations and try to see whether I can get a collision cone from my intuitive understanding of what I see here. So now look at this. This cone, that is, so I draw a cone from A to this object B so that it contains this circle. So I call it the C cone. Why I call it a C cone is to avoid confusion, because many people call this as the collision cone. So to avoid that, I call it a C cone. Now what I do is that I take the velocity of B, shift it to the point A, and shift this cone to the tip of that velocity here. Correct? And then what I do is I take the VA, draw a circle around it, and place the circle here. And if I do so, the intersection of that circle on these two lines, that is the boundary of the shifted C cone, will give me the collision cone. Looks like magic? Not really. I'll explain to you. It's actually just dependent on the relative velocity concept. But just to tell you a little more about this, first let me tell you another concept which is called velocity obstacles. So in the previous case, we said that the speed of A remains the same. It's only the direction that changes. What if we allow the speed of A to also change along with its direction? If that happens, then I have something called a velocity obstacle, which is nothing but the shifted C cone. Okay? And any velocity vector of A that lies in this cone will lead to a collision with B. Again, is it magic? Not really. All we did is that if you look at the relative velocity VB minus VA in vectorial term, you will see that any velocity vector which is here, if you take that minus VA minus that VB, it will always lie on a point which is within this C, which means that it is going to hit the top. That's simple as that. So all velocity vectors of A here can lead to a collision, because if you take the VB minus VA, it will lie in this C. So it will. That's a simple idea. So we have the notion of collision cone and we have the notion of velocity obstacle. In collision cone, the speed remains constant. In velocity obstacle, you can play around with the speed also. Okay. Till now, I have managed to do all this without any equations. I hope that continues. The question is that can we extend this to higher dimensional spaces, collision cone idea? Yes, it does. As long as we are able to define the C cone, we should be able to do so. So here is an example of a point and sphere, point and a spheroid, a point and an object which can be represented with a cone of circular cross-section or elliptical cross-section. It can be done. More complicated objects can also be worked out. You have to take slices and do that, but we will not go into too much detail. We understand that we can define the question, the notion of a collision cone or a velocity obstacle to show when A collides with B or A intercepts B. You may say that you took only A as a point object and B as a circle. How does it work? What about A is also a circle? That's all right. All you have to do is transfer the radius of A to B. So call it, if RB is the radius of B, then you consider a point object and another object B which has a radius of RA plus R. So this is, people who work on configuration space learn this, but it is also intuitive that you can always consider one of the objects as a point and you will be able to do this. Okay. Now let us go to the AERObotics problem. We have done all this with, just point objects, and we are talking about the intercept problem and so on. How do we apply it to AERObotics problem? So the problem that we are going to look at in this talk is look at this. There is a drone here where with a cable hanging from it, and to the cable there is a ball here. I think the ball is a yellow colored ball which is hanging here. And I want to fly a drone like this with a manipulator like this which will catch this ball. Okay, so this is what we are going to grab. Remember that when the drone is flying, this cable is also swinging. The ball is swinging. The drone, whatever trajectory it takes, the ball will also take a similar trajectory with a swing attached. Right? So the problem is not that very easy. It's like a maneuvering target. Nothing is moving in a straight line and so on. So we have to solve this problem. So let's see, how do we solve this problem? So we do this, and on the right side, I apologize to you for these equations. I will explain them to you, but I will not bother you too much about this. So now let's look at this problem. So I have a gripper or a grabber, which is modeled as a circle like this, and there is a ball which is another circle like this. Now, unlike the interception problem, there is a difference here in the sense that in the interception problem, I wanted the point A to hit any point in B. Here, that is not the case. I want that the gripper should hit this ball so that the ball is well within the gripper. Only then it can grab it, correct? So that can also be solved by taking the difference in the two radius and say that this is the gripper, and we can also transfer this to this point. It will be the same problem. But this is now not RA plus RB, but it is actually RA minus RB is the radius, which ensures that if the gripper is anywhere, if the gripper is such that the target hits, the ball hits the gripper, then the ball would be inside. So this R equivalent that we are talking about is the R of the gripper minus R of the ball. And this one you can ignore for the time being. This is actually the mathematical condition in 3D that tells you whether the given initial conditions and constant speeds, whether this gripper will be able to grab the ball. So there is a difference between the intercept, the missile aircraft, and this problem. Here we have an image plane. So there is a drone here. There is a camera here at this point, and this camera is actually looking at this ball. And this is the image plane. So if you project the image of the ball onto the image plane, you will see this is what happens. And this is the optical axis of the camera. So this is the information that we have with which we will try to conduct our guidance problem, right? So the guidance strategy must look into this part, that a visual guidance strategy is where the interceptor moves towards the target along the line of sight. This is one thing that can be done. And the grabber UAV applies a velocity which is parallel to the line joining the camera center. At the same time, it also applies a yaw rate command to bring the ball to the center of the image. So all this is what the guidance strategy does. And you will see that this is actually related to the collision cone idea that we had earlier. So this is the block diagram of the guidance and control architecture. I will not go too much into the details of this, but the image from the monocular camera is processed to generate the guidance command, and that guidance command is now fed into the drone and it makes the necessary motion. It's not very simple in the sense that because the drone itself is not carrying the camera that is used for catching the ball. We will see where that camera is. So if you look at this picture, you will see that this is the drone and this is the manipulator that is sticking out of the drone, and the camera is somewhere here on the manipulator, on the grabber. So this is called eye in the hand kind of thing, right? So if you want to catch something, you put the camera on your hand and you try to do this. Okay. So then the same image plane, optical axis, and the ball is there. So now the drone has to do a search of the sky to look at where the ball is. Once it detects the ball, it starts tracking. So there's a lot of work that has to be done before all this can be done. We'll not go into the details of that, but we have to get the data set, train the network to identify the ball, and then start tracking it. So this is the block diagram that we use for the detection and tracking. There is a complete mission flow. The mission's flow has exploration of the sky to identify the ball. It may happen that the UAV may miss the ball after some time. It might be tracking because the ball is moving in a very strange way. Usually it is moving in a figure of 8. It may miss, and again it has to search. So there is a disconnect and the whole process needs to be started. So that's what happens here. In fact, there are some simulations that you can see where the target and interceptors are moving. These are MATLAB simulations. They're not real things. They're just MATLAB simulation. And as you know, everything succeeds when you do it in simulation. So here things succeed. So the target and interceptor move around. So tracking happens, then grabbing happens. This is a case when the target is a high-speed target, higher than the speed of the drone. So this is where the catcher drone or the grabber drone actually tries to meet the target head on. So if it tries to chase the target, it will never be able to catch it because it's faster. So it meets head on. So this is what. Now these are some of the things that happens in this particular simulations. We actually had 2 drones which are doing this. So, and they are transferring control from one to the other. So wherever there is a GSA is a grabbing standby approach. So a ball grabbing happens, but it fails. So it again goes into GSA, and the second one does this. So it transfers role from one to the other. Here, the first one failed at this point. The second one took over, and it was able to catch the ball, and then it landed. So the roles as they change from standby to a tracking, from tracking to standby to grabbing to standby, and so on, are shown here. The points where the changes happen are also given here. This is the zoomed version of the ball grabbing part of it. I'm not showing animations here because I have better things to show you later. So after doing all the MATLAB, we actually did it in the ROS gazebo implementation, which is obviously the thing that you need to do before you actually go for an actual implementation to make sure that whatever you are doing actually works. So we did that also. Again, I'm not showing you any animations here. We also need something called an operation management system. This operation management system is something that tries to handle, to control the whole operation from through a base station to the drones. The drones are autonomous, but they have to be given some commands at intermediate times to take care of it. We will not go too much into the details of this, but this was a necessary thing that has to be designed and put in the ground control station so that the UAVs can work freely. The major components that we use for this particular problem is a DJI M600 hexacopter here. We have this NVIDIA Jetson. There are two cameras that are there, one on the drone, the other on the arm. A major part of the project was also on the grabber design or the catcher design, the tool that is made. So first we made something like this, which has a mechanism by which, you know, the hand can move like this. You can see that this can actually move and catch the ball. Then we decided, we found that this is going to be rather inefficient to do so. You need actuators and all that. Instead of that, we put up something like a frame with a net on it, which after several redesigns, it took on this kind of looks. And there is also a small camera here. This camera is used for the guidance as well as to detect whether the ball is inside or not. Okay, so detection of whether grabbing has happened or not. So the design steps for this are as follows. We did the CAD model of this. We actually designed all this. So this is the plate for detection. So this plate was actually put at the bottom at the first thing. And then there are limit switches. I mean, the whole lot of design activity went on to make sure that when the ball is inside the grabber, the drone knows that it has caught the ball. So this is the camera. Now you have to decide what should be the size of your grabber. I mean, you can't have a very huge one because the drone is small. It cannot have too small because then your accuracy becomes too much demand on your system. So we designed something that is about 3 balls apart. So even if the ball swings, so we took the swing of the ball into account and said that even if the ball swings, we are able to grab it. So we designed the volume of the grabber based on that. So we also looked at the forces because, you know, when the ball is caught, there is a force that goes into this, and we don't want our carbon fiber rod to break. So that is also, we did all the force calculator, cantilever loading and all that. Just to show you that doing something like this is not just writing software program, but you have to actually design things and make them work. The final design is something like this. So we have a rack and pinion mechanism, which extends the arm and pulls it in, all that. And this is the end effector of the rack and pinion mechanism. So this is basically the final design on which the net was. So once we assemble everything and we are ready to fly, so this is the drone, there's an onboard computer, there's a camera here, there's a linear actuator manipulator, and there is a grabber with a grab detector attached to it. We have to test it. So where do we test? We created a In our airfield, we created a test bed where we have both a flying ball and also a ball which is stationary. So for that, we had a contraption from which the ball is hanging. And we tried to do this. So this is the test bed. This is the IISc airfield. Well, it doesn't exist. I mean, it does exist now, but not this much. But when we did the experiment, it was there. It's a pretty large airfield in which we carried out all these experiments. So the first successful experiment that happened was like this, in which the ball, this is a red ball. Initially, we used a red ball. That ball was detected. It was, you put a bounding box around it. It's a bounding circle actually. And we came close enough to grab them. And when we took this video from the ground, this is what it looked like. So this is the drone with the ball hanging. This is the drone with the extended grabbing mechanism. It comes close to this, detaches it, and it lands. Okay. So if you look at a zoomed version of this, then this is what you see. You see that the drone is approaching this ball, grabbing it, pulling it, and detaching it. From ground, this is what it looks like. This has been taken from another drone. We took this picture. And then it comes and drops the ball into this designated box. It actually identifies the position of the box and drops it. Right. So all this is just static pictures and me claiming that it happened, right? So it is time for me to show you that it actually happened. We have several videos and I'll show you only one of them because there's no time, but if you go to YouTube, you'll see the rest of it. So this is what we will see. Okay, let us see. Yeah. So there are two UAVs which are initially trying to identify the ball. So these are the two UAVs. They are exploring the sky to identify the ball. So that will soon happen. So there is an exploration pattern that they follow. And you can see that one of them has now detected the drone and the ball hanging from it. The moment that happens, the first UAV goes into standby mode and the second UAV starts following the target. It tracks the target and moves towards it. And as it does so, you can see that this is the ball. I'm not sure if it is visible, but I'm following the ball here. This drone is actually moving in a figure of 8 trajectory, and this drone is following it. And after some time, it comes close to this, gets closer, grabs the ball, detaches it, and then it comes and lands. So after it grabs, there's a grab detection, and then it comes and lands. So this is what happens. So we have been able to catch something in the air. I have to acknowledge that there was a very large team of people who did this, very young people from my lab, from other labs in the institute, from TCS Innovation Lab in Bengaluru and Kolkata. They also joined us in this. I'm not giving individual names because I might miss quite a few of them because it's a large number. But if you look at the papers that came out of all this work, you'll find them as authors here. So this paper is it's a 50-page paper that talks about the whole process that was followed to execute this particular project. This is the paper that talks about the guidance part of it, that how monocular camera was used for the guidance. And it is different from what is used for the missile target, although the concepts used are the same. So the details of that are given in this paper. This paper talks about the design and integration of the grabber mechanism and how that was done. The whole design of that is given here. There are several other papers that have also come up here. Some of them are very seminal papers that talk about the collision cone concept and the velocity obstacle constant concept and so on. And there are several other papers that came out of this. So if you have interest in knowing about it, you will know this. You will be able to read it from here. And with this, I thank you, and I'm open for questions.
Thank you very much
Okay.
for the great talk.
Thanks. Yeah, thanks a lot, Professor Ghosh, for a great talk. I hope everyone enjoyed it, and it's great to see the way you actually split it into conceptualizing and then testing in simulation. You basically took us through the journey of the project. So we are open for questions. If anyone has a question, you can raise your hand, and then you can just unmute and go ahead with the question. I'll wait for some audience questions. Any students who want to ask a question to go ahead with? You can unmute and go ahead with the question, like if you don't mind talking. Shailesh. Okay. Oh, mic problem. Okay, I'll take your question. Let me ask Rahul to go ahead with this question, and then I'll come back to Shailesh's question. Rahul,
Hello, am I audible?
Yeah.
Thank you, sir, for the talk. Sir, can you move to that slide where two drones are actually doing a particular grab task, where you have this timeline thing? Can you move back?
In the video?
No, it was a photo. Can you move back?
Yeah, I got it. Yes, surely. This one.
This one. Yes, this one. Yes.
Correct. Yeah.
So in this, if I understand correctly, two particular robots are doing a collaborative task. Like if one fails, then other comes in. Like how are they communicating? Like when
the collaboration is actually pretty limited in the sense that they are not exchanging information as such, except for saying that I have lost a ball.
Okay.
And the other one goes into tracking mode. So that happens through this operation management system. So they do that. But apart from that, both of them are actually working autonomously. But if one of them detects a ball, then it starts tracking and other goes into the standby mode.
Okay.
If it loses it, then the second one takes over.
Okay. So if in this particular diagram, for example, drone 2 goes to ball tracking. So that means it just keeps a track of the position of the ball where it is going, right? Just for in case it has to come in the picture and then do the... And then, and also both the algorithms are on GSA at the same time. What does that mean? Like, for example,
So this is the grabbing standby approach, so that it's actually in a position where it can move into the grabbing phase.
Okay.
But for example, in the drone 1 case, you can see that after GSA, it actually grabs the ball, but it fails. It fails to grab. The second one is also in the grabbing standby position, and once the first drone fails, the second drone now goes for the grabbing, and it succeeds.
Okay, so how do we decide here, like who is the lead agent, who is the like backward supporting agent, or like is it depending on the position and the cost?
It's depending on the position, and yes, I understand that. Yes, I understand the question. So there could be a conflict, like if both of them tries to make a bid for the grabbing, that doesn't happen because of the operation management system does not allow that to happen.
Okay.
So the
I just
grabbing
wanted to
operation
understand.
is disjoint.
Okay, sure. Thank you, sir. Thank you.
Thanks, Rahul. So Shailesh, I think your question was on communication between two drones. I think it's addressed as of now. Sinaya, do you want to unmute and ask your question, or you want me to read it? Sinaya Nayak?
Sandeep, I think you can read it.
Yeah, sure. I think the question says, like, not to undermine the great contribution, but then wouldn't it be better if we have a ball dropped in free fall instead of being tied. With the string, the ball's motion stays fairly constrained, almost like static target, but wouldn't it be a better test of the dynamic system if we are grabbing the free falling ball?
Yeah, I quite agree that the problem can be made more complicated, but what I most probably did not cover here, I did mention at the end, is that this was actually part of an international robotics challenge that we took part in, where it was required that the ball hangs from a drone, and this drone executes a figure-of-8 uh, trajectory at a very high speed. And we are supposed to grab that. So that was the problem we were addressing here.
Okay. Yeah. Any more questions from students? I have a quick question. I can ask that. Basically, like, sir, in aerial interception tasks, like there can be, as already talked about, like there is also situations where you have there's uncertainty about the target's motion, and also there is sensing delays. So can you comment on that? Like how can you adapt for those two challenges? Because those can sensing delay maybe act more into
Yeah, I think important questions, and they were also things that we addressed in this. So there's a lot of work that I did not cover. So one of them takes the delay into account when it designs the guidance strategy. The EKF was used to predict or estimate the target's motion, and use that in designing the guidance law as a predictive mechanism. So some of which is there in the paper. I did not add it here, but yes, those are definitely questions that also came to us, and we had to redesign our guidance law to take into account these and other constraints as well.
Okay. Yeah. Thanks.
Yes. Professor Ghosh, if I can ask a quick question. Sorry, did I cut someone short there?
There was a question from Avijit, but you can go ahead.
Go ahead. If you're speaking, please go ahead.
Avijit, do you want to speak?
Hello, can you hear me?
Yes.
Yes. Thank you for a very nice presentation, sir. I mean, when I was listening your talk, I mean, the first thing came in my mind was when I was during my childhood, I used to run along to catch the flights, the kites, and how many kites I could have catch with this system if it exists that time. Just for a lighter note, since you have assumed kind of constant magnitude velocity throughout, I would like to have your insight, since it's a real experiment. Was it difficult to maintain this assumption, or how you managed this, and what sort of time frame this project took altogether? It's a huge task all around.
No, we did not assume a constant speed. That is obviously not possible. It's not practical. So drones can fly at anywhere between 0 speed to its limit. So we took all that into account. So when the guidance law was designed, it took into account the speeds of the drone that is necessary. That's the reason why I talked about the velocity obstacle also, where we considered different speeds. So in the guidance law design, we took that into account too. The drones are not always flying at its maximum speed, nor was it. In fact, it has to hover momentarily at the point when it is grabbing. So the speed variations were there. As for the time period for which this work happened, it's more than 1.5 years that we took to complete this, because there was an enormous amount of work that had to be done. So what you saw is only the end product of it.
Yes.
I would like to just add something more to it. That work in different ways is still continuing. For example, we are also now designing, at present, we are actually designing flexible manipulators that can be attached to drones. Not the kind of manipulator that I showed you, but it's more like, if you remember one of the slides, let me show you that. Yeah, so if you look at this, this one, like an elephant trunk, right?
Yes.
So one of my collaborators, Professor Pradipta Biswas, and I are, with help of a PhD student, are designing these kind of manipulators. We have already designed one, and it's working well. Only thing is that it is still working with a hovering drone, but not a flying one. So we are getting there. So whatever we have learned from this project, we have now doing more things with it.
Okay.
Very nice work, sir. Thank you. Thank you for
Thanks, Abhijit.
Yes.
Aditya, do you want to go with your question? There are two more questions I'll take after yours.
Okay. Yeah, Professor Ghosh, nice talk, as usual. Loved it. So a quick question. So you did this for the MBSR competition and where they flew a figure of it. So what was not clear to me, I may have missed it. Was the profile for the figure of eight fixed? I mean, was it something you could explicitly use in the optimization subject to some uncertainties, or did you have to learn the figure?
No,
or was that not
we
an option?
knew it was just a figure of 8, but there is nothing that we could get out of this. Like, it was not a very fixed kind of trajectory.
Okay.
So they had programmed it in such a way that the figure 8 would keep shifting. It is still within the stadium arena, but it would shift. So we could not get any information about its trajectory apart from what we can predict.
Okay. Okay. So when you go for when the drone would go for the grab, it was using sort of the guidance laws that you showed at the outset without assuming any specific profile for the
Yes,
for the evader drone, whatever you call it. Okay. Okay. And with this algorithm, do you like have guarantees on the time of capture?
No, we can't. We can have guarantees if the target is moving in a predefined way. But without that, we cannot have a guarantee because there are too many uncertainties. So what happened is that we did a lot of experiments that never we had an experiment where we grabbed it the first time. I mean, we missed, then we came back again, we missed, we came back like that.
Okay.
So you cannot really guarantee anything like that.
Okay.
Fair enough. Fair enough. Thanks, sir.
Thanks, Aditya. Yeah. There's a question from Prashant Devarati. Do monocular estimates distance of balls? Like, can you use monocular camera for estimating distance of the ball? If yes, which technique was used?
So that was actually a much simpler thing to do because we knew the size of the ball. So from there we can identify the depth or the distance. So actually, if you look at that paper that I have given there, it is that whole depth estimation algorithm is there. It's actually pretty simple because you just have to do some data set processing and you know the size of the ball, so you can know at what distance it is.
Okay, thanks. Sujit, do you want to go with the question? There's one more question. I'll go after you.
Yeah, so great work again. So are there any lessons learned that while doing this kind of an experiments, what not to do or when to do?
Lots of lessons, actually. I'm glad you asked. For example, since it was an international challenge, I think you may like to know what happened. Did we do anything there? And this is where the biggest lesson came to us, that the communication system that they had, so this was done in Abu Dhabi.
Yeah.
So we went from Bangalore to there, and at the time of the challenge being executed, we realized that they have divided the arena into 3 communication zones, and these 3 have different frequencies. One of those frequencies, or 2 of them, are not part of our communication system because the Indian government has restrictions on what kind of communication frequency you can use. And this was a forbidden frequency. So that is the reason I did not show you those videos. We came close to the ball, but before we can go for the grab, it went into the region where the communication did not work. So we had a problem there. So that is the biggest lesson, that we did not know about it. So we should have found out about it. No point in blaming others. We should have done it. But even if we had done it, whether we would have been able to solve that problem, we do not know, because all the experiments were done here in India, and we could not use the prohibited communication frequency, which were not told to us.
Yeah, that's true.
Many of the teams who went there and the one who won the thing, they actually camped in Abu Dhabi for several months to do this.
Okay.
So they knew all the frequencies that were needed there. We did. So that was one lesson that happened. The second lesson I would say is that we have to have a large number of trials before we go into any of these challenges, or for any other thing for that matter. For example, if there is a startup that's trying to produce something that is related to drones, my advice is to do as many tests as you can, running into tens of them, not just 3 or 4 or something like that. 10, 20, 30, 50, 100. Do them, because you do not know where the failures can come from. And every time you fail, you actually win, because you know where the failure is coming from, and you work against it. All that we could not do because of limited resources that we had here. Our drones crashed, so you have to rebuild it, you have to buy them, lots of things. I think some of the participants here were also a part of that particular experiment, so they know the heartbreaks that we went through. Towards the end, we were working 24/7. We had floodlights in our airfield and working there on that. So yeah,
Nice.
it was a great experience.
There are two more questions. I'll just finish with that. I think we are running short of time. So there's one question by Bharat Bhushan. How is career in humanoid robotics? Recommend fundamental books. I think one thing we can do is, as part of Robotic Cafe, we can add a resource page where we'll kind of collect resources from people and maybe add it for students' benefit. That we will do. I don't know if this was the question relevant to the talk now, but there's a question by Pranjal Upadhyay. And the question is, I had a quick doubt regarding the string handling during ball capture. As the string becomes slack, it might get entangled with one of the drones. Are we explicitly controlling for this situation, or is it being handled through the experimental design?
Yeah, it's a very relevant question, but we did not face that problem because we extended the arm to the extent that it grabbed the ball, and the other UAV, which was carrying the ball, moved away. So we did not have a case where the cable gets entangled with our drone. But yes, it was one of the things that we also thought of, and that is why we had a long arm, so that the ball or the cable does not entangle with our propellers and things like that.
Okay, I think that brings us to the end of the talk today. And then let's thank Professor Ghosh once again, and thank you for accepting our invite and like giving such a great talk to start the series. So you have set the mark up high. So we hope we get.
Thank you very much.
Thank you for the further.
I believe I have a very wonderful audience, and I hope all of you come back and listen to other people who are going to talk about robotics here.
Thank you, Professor Ghosh. There are a couple of logistic announcements for all the listeners. So we have I'll just share my screen. So are you able to see my screen? Yeah.
Yeah.
So if you go to the web page of Robotics Cafe, like you can actually look at this for receiving updates. Please join our mailing list. And other than that, one more important, and our schedules are put up on this page. So we'll update this further this week, and we have great speakers actually scheduled, like 5 speakers already scheduled. And under the opportunities is where we are posting some opportunities for the students to apply for. And we also have a location for faculty and industry to put or inform us about the opportunities if you want to advertise it further. So please make use of this this place for that, and you can fill in the form here if you have an opportunity that you want to announce, and students can go through the list of opportunities. We are yet in the process of updating this list. Yeah, I think that's from our end. And any final notes, Sujit, that you want to?
No, that's all. Thank you.
Okay. Yeah.
Ghosh.
Thank you everyone for joining.
And it's a good kickoff for the Robotics Cafe. And thank you all the audience for joining us, without which it would have been a really not that interesting. Yeah. Thank you very much.
So